Industrial robots may have come a long way, but they'll have to go a lot further before they can imitate everything our bodies can do. So what makes the human body such a good piece of engineering? Fitness machines, we all use them, or at least think that we ought to. But you can't build up muscles without a framework to build on. Let's look at the body, not for beauty, but for design. Like all good engineering, we need a blueprint. And let's see what it can do. But the body is a mechanical structure, a complicated one. So what are the important components? Take a simple movement, a pull-up. Each arm acts as a pair of levers. Muscles generate the force lifting the body. Ligaments and tendons string it all together. Complicated, but in every movement we rely on rigid components to transmit the force. Just try taking away the bones. With exercise, we can develop our muscles. Large muscles can create larger forces. Forces are created by the muscles contracting, but they can't produce useful movement unless there's something strong and stiff to pull against. That's why we're going to concentrate on the body's strongest structure, the bones. Every time we move, our body is subject to forces, often several forces in different directions. On a trapeze, the arms are put under tension. The body exerts a force in a downward direction, made of an elastic material, and it would stretch. Some body tissues are elastic. Muscles certainly stretch, but not bones. If you do a handspring, the forces act in the opposite direction. Both arms and legs are compressed, but they don't change length. Bone is strong in tension and compression. Muscles to produce forces, but bones to withstand and transmit forces. Imagine a body without bones. Wouldn't give much for our chances of survival. But some organisms can survive as a fluid-filled sac. What's their secret? Our bones can withstand several times our body weight. Okay, so they're strong, but how strong? Here's a typical long bone. Not from one of the acrobats, it's a cow's leg. How can we test its strength? First problem is the shape. Complex. When a cow is standing, forces are transmitted vertically through the bone. So the ends of this bone are set in a metal alloy with a low melting point. This stops forces getting concentrated and makes sure the strength of the bone is tested in the correct direction. Now, how strong is it? When when pressed, it breaks at 36,000 newtons. But how strong is that compared with, say, a rod of steel? To make a fair comparison, better make sure the metal has the same mass and length as the bone. Like to take an educated guess? Not much more than half as strong. But as you saw, bone isn't a solid rod, so we ought to improve our comparison. Here's a hollow cylinder, same mass and dimensions as the bone. Stronger or weaker? So it's stronger than the solid metal, but not as strong as the bone. Surprised? For the same mass, bone is strong, but it might not still be the perfect comparison. Bone isn't hollow, it's filled with bone marrow. It doesn't look very strong, but maybe it contributes to the total strength of the bone. Take a thin steel tube. It's not that strong. Fill it up with plastic foam. Let it set. And the filled tube is stronger. But it's only foam. How can it make something that much stronger? Right then, bone is surprisingly strong for its mass, but what is it that makes it so strong? Here's a bone under a microscope. Unlike a metal, it isn't uniform. If we look under higher magnification, we can see that there are fibres within the bone. Does that remind you of any other material? It's quite like glass reinforced plastic, glass fibres set in a polymer matrix. But whatever else it is, bone isn't glass and plastic. So what are the fibres, and what are they set in? Look at this piece of bone. And this one. Two bones, different properties. They don't behave like ordinary bone. One brittle, the other flexible. And they don't even look like ordinary bone. So what's caused the change in properties? Put a bone in acid. It fizzes slowly. Leave it there for a long time, and it becomes flexible. Something has dissolved in the acid. But what? Well, here's a clue. Put a piece of chalk in acid. It fizzes a lot more vigorously. Chalk is calcium carbonate, which reacts with the acid to produce carbon dioxide gas, the fizz, and calcium chloride, which is soluble. So chalk could be a component of bone. But how can we test that calcium is present? Put a calcium compound in a flame, it produces a red colour. In this case, it's calcium nitrate. So how about bone? Same red colour. So there is calcium in bone. Removing the calcium makes the bone flexible. Only the fibres are left. So what do they do? Well, here's a substance made from calcium compounds without any fibres. Concrete. Hit it hard and it fractures easily. And we've already seen some bones that shatter like this. What happened to them? They were baked at high temperatures. And it's much quicker, of course, if you use smaller bones. The heat destroys the fibres, leaving only the calcium compounds. Without the fibres, the bone is brittle. But what about whole bones? They can be broken. If you have the force. Painful, yes, but it's pretty difficult to break a leg. Look Look at the X-ray. The break looks pretty smooth, but in fact the edges are jagged. If bone is hit from the side, every time it comes to the fibre, it's diverted. The force is reduced. In most cases, this would stop the fracture before the bone breaks. So fibres make bone harder to crack. So what can we learn from the way bones are constructed? We've already seen that concrete is not as tough as it might be. So what's the steel for in reinforced concrete? So bones do break, we've got that, but not always as cleanly as the last one we saw. In particularly bad accidents, there are many breaks. This arm would heal, for instance, but be permanently crooked. We can mend badly broken bones. One approach is to pin the bone fragments back together with metal screws and plates. Here you can see the finished result on an X-ray. But could we just use any metal for these plates? What sort of environment is the body for a metal? Oxygen, water and carbon dioxide are all present in body fluids. Not so good. That sounds like a great combination for corroding a metal. So what material would you suggest? Mending a badly broken bone is one thing. It can be as good as new. But what about replacing a bone? You might ask, why would we want to? Well, like any machine, the body has parts that wear out. For example, many elderly people suffer from problems with their hip joints. Painful, yes, but is there an answer? First, we have to ask the right question. What does a hip joint have to do? Like a mechanical joint on a car, it has to be free to move in all directions. This universal joint isn't the same as a hip, but you can see the similarities. The ball at the end of the leg bone rotates freely in a socket. This is what seizes up in elderly people. Why? Inside any joint, the ends of the bone are smooth and covered with a shiny, slippery membrane. As people get older, both bone and membrane deteriorate. We could replace the ball of bone with a ball of metal. But what about the surface of the ball? Shiny, yes, but in a machine where metal meets metal, we need to use a lubricant like oil. But you can't put an oil cap on Granny's hip, can you? So how can we make the surface slippery? With an egg? No, not the egg, the frying pan. Non-stick and unreactive too. The frying pan is coated in a plastic. Like all polymers, it is a long-chain molecule with a backbone of carbon atoms. But this polymer is different. It's called polytetrafluoroethene, PTFE for short. 2 fluorine atoms are attached to every carbon. They envelop the chain. Coat something with PTFE, and any material coming into contact with it slides over these slippery chains. As slippery, in fact, as the membrane that coats healthy hip bones. So by mimicking the properties of the body's own materials, we can replace a bone. But what about a whole leg?
Now this is achieved by balancing...
First challenge, what material? Metal? We've already seen that that would present a problem. To be as strong as bone, it would have to be heavier. But a person wearing an artificial limb can't produce as much force. So we're looking for something even lighter than bone and as strong.
Okay.
Light and strong. The same combination of properties as bone, but more so. So what is it? It looks quite like bone, a tube, and it breaks quite like bone. jagged edges. In fact, its structure is quite similar, fibres set in a matrix. But the fibres are a very advanced type of polymer called carbon fibre. Can you see any advantage to using this material inside the body? Right, let's move the emphasis away from the structure of single bones. How are groups of bones arranged in the body to make larger structures, from materials to engineering? Bones are linked into a complex structure, we know that much, but it's no use the individual bones being strong if the structure is weak. Plus it has to be flexible and provide protection. The different soft tissues of the body are protected in different ways. Heart, lungs, liver, guts. They're all inside this protective cage. Why a cage? Well, think about weight saving again. Solid might be tougher, but how heavy would it be? Knights in armour weren't exactly known for their speed and agility. Adapting a successful structure is good engineering. But can we copy the ribcage? Here's an old racing car. The design is very light and strong. It's called a space frame. Struts and rods of tubular steel welded into a cage. This pattern of struts is quite common, and designers have found that the pattern is the lightest way of resisting forces from different directions. Take a smaller space frame, a box braced with diagonal struts. Whichever direction you hit it from, it can withstand the force, distributing it through the frame. But if it's so good, why aren't our ribs constructed exactly like this? Because unlike the car or bridge, our ribs have another task. We've just got to breathe. Our cage has to be strong and flexible. Some things, though, are just too delicate to be protected by a cage. The brain is our most vulnerable organ and very soft. Couldn't risk something pushing between the bars of a cage. So it's cased in solid bone. Very useful in the car and on the pitch. In withstanding forces, it works like a crash helmet. The force of an impact is distributed across the whole surface. Modern racing cars are built in the same way. No frame. The whole strength of the structure is carried on the surface. So here at Le Mans, the driver has a skull, inside a skull, inside a skull. Foam-filled tubes, space frames, artificial limbs, racing cars. The body provides us with some great design ideas, but it doesn't give us many clues when it comes to the secret of flying. It certainly isn't just a question of strapping on a pair of wings and flapping. But if we can't be inspired by our bodies, where should we look? What do you need for an animal to fly? Birds are just bone and muscle too. But maybe there's a difference. What's their secret? Fitness machines, we all use them, or at least think that we ought to. But you can't build up muscles without a framework to build on. Let's look at the body, not for beauty, but for design. Like all good engineering, we need a blueprint. And let's see what it can do. But the body is a mechanical structure, a complicated one. With exercise, we can develop our muscles. Large muscles can create larger forces. Forces are created by the muscles contracting, but they can't produce useful movement unless there's something strong and stiff to pull against. That's why we're going to concentrate on the body's strongest structure, the bones. Every time we move, our body is subject to forces, often several forces in different directions. So what are the important components? Take a simple movement, a pull-up. Each arm acts as a pair of levers. Muscles generate the force lifting the body. Ligaments and tendons string it all together. Complicated, but in every movement, we rely on rigid components to transmit the force. Just try taking away the bones. Industrial robots may have come a long way, but they'll have to go a lot further before they can imitate everything our bodies can do. So what makes the human body such a good piece of engineering?